The paper we're jumping into today is ThetaEvolve, test time learning on open problems. And honestly, if you're following how AI is pushing the boundaries of science, this one, well, it completely changes the rules for efficiency.
It really does. I mean, the whole mission here seems to be about challenging the status quo. For a while now, all the big breakthroughs have come from these enormous closed-source models. Your Geminis, your Claudes. ThetaEvolve is an open-source framework that says, no, the model shouldn't just do the search, it should learn the strategy.
And get this, here's the big takeaway right up front. ThetaEvolve let a pretty small, open-source, 8 billion parameter model, DeepSeek R1 0528 Qwen 38b, do something. Well, something unprecedented. It set new best-known bounds on two super hard open math problems. Circle packing, which we'll just call CP.
And the first autocorrelation inequality, or theta.
That's the punchline right there. A small, accessible model just outmaneuvered a whole team of the world's biggest, most expensive proprietary models. And it did it fast.
Incredibly fast.
The speed difference is, it's almost hard to believe. For circle packing, the program that ThetaEvolve found gets the best solution in just 3 seconds. 3. The old record holder from ShinkEvolve needed an ensemble of 6 advanced models and took 75 seconds.
And that efficiency is the whole story. The real innovation here isn't just a clever prompt. It's actually integrating reinforcement learning RL right into the evolution loop while it's running. They're using algorithms like GRPO to update the model's own parameters, teaching it how to be a better scientist on the fly.
Okay, let's unpack that because that's a huge shift from how these things used to work. To really get why ThetaEvolve is so clever, we have to look at what came before it, right? The AlphaEvolve pipeline.
Exactly. AlphaEvolve was the blueprint. It's a loop. You have a database of programs, you pick a parent program, and you ask an LLM to suggest changes to make it better at something, like maximizing the circle radii in the CP problem.
But, and this is the key, it was all inference only. The system was basically just a very, very fancy prompt loop. The model itself never changed. It never learned from its wins or its failures.
Right. And since the LLM wasn't learning, you had to rely on 2 really expensive things, just the raw power of a giant model and running these ensembles, getting 4 or 6 huge models to vote on the next step. It sort of created this idea that only the biggest labs with the biggest models could do this kind of research.
And even the open source versions like OpenEvolve were super complex. They had tons of hyperparameters you had to tune, and you never really knew if it was working because of a smart prompt or some random setting you tweaked. The ThetaEvolve just cuts through all that.
It does. Their whole philosophy was, let's simplify the LLM side of things and then massively scale up the infrastructure.
The simplification part is huge for anyone who has to pay the bills. They just got rid of the ensembles. One LLM, a smaller one too. And they even added this optional simplified prompting called iterative refinement.
And that's a neat trick. The old way might feed the model the parent program, plus a bunch of other good ones from the past for context. Iterative refinement just says, you know what, let's often just give it the parent program. That shortens the prompt, which saves time and money over a long run, and it turns out it works just fine.
But the real architectural magic is how they dealt with the compute bottleneck. The old systems were asynchronous and sequential. You'd ask for one new program, wait for the model to think, get the result, test it, and then ask for the next one.
Which, if you're an ML engineer, you're just screaming inside, right? You've got these powerful GPUs that are great at batching, and you're not using them. It's so inefficient.
So ThetaEvolve flips that entirely. It uses batch sampling. Instead of asking for one program at a time, it samples a batch of 32 parent programs all at once. And for each of those 32, it generates 16 new versions.
You're suddenly getting 512 new candidate programs in a single step. It's like going from a craftsman's workshop to a full-scale factory floor. The throughput just skyrockets.
The numbers are wild. An OpenEvolve run took over 63 hours. The ThetaEvolve inference-only run, doing the same amount of work.
Just 5.4 hours.
A 10-fold speed up. That's not just a little better, that's what makes this kind of research possible on normal hardware over a weekend.
But wait, if you're suddenly generating this massive volume of programs, how do you make sure you're not just creating a flood of garbage?
That's where the other scaling piece comes in. The program database. OpenEvolve kept a tiny population of like 70 programs. ThetaEvolve scales that up to 10,000.
And their tests showed that this is critical. When you crank up the compute and generate more programs per second, you absolutely have to increase the population size to maintain diversity. Otherwise, the model just keeps iterating on the same few ideas.
So the speed lets you explore a huge space, and the giant database makes sure that space is actually diverse and interesting.
Precisely. And now we get to the secret sauce. The part that turns this from a fast search tool into a genuinely intelligent agent. The reinforcement learning. They treat the whole pipeline as this dynamic, adaptive environment for RL training.
Okay, so the system is literally learning from its own experience as it works. But if the search is already 10 times faster, why do you even need the RL part?
It's because of how these open problems work. When you're just getting started, it's pretty easy to find small improvements. But when you get really, really close to the best-known solution, the state-of-the-art finding that next tiny improvement is brutally hard.
The stagnation problem. The model just gets stuck.
Exactly. It starts giving you lazy outputs. It'll just spit back the program you gave it, or it'll generate code that doesn't even compile. If your only reward is for making progress, the training signal gets way too sparse. You need to punish that kind of lazy behavior.
Which brings us to their lazy penalty system. This, I think, is just brilliant. They don't just reward good ideas, they actively penalize bad habits.
It's a whole system of negative rewards. For example, if the model generates a code block that's identical to the parent, that's a penalty. If the code compiles but the program is functionally the same, that's another penalty.
So they're teaching it. You have to try something new, and it has to be valid. And I love this detail. If the program it creates is a duplicate of any of the 10,000 programs already in the database, even if it's a good one, it gets a penalty. That forces it to keep exploring.
It's a really smart way to keep the search moving forward. And for some of the trickiest problems, they went even further. On tasks where the objective score is in a super narrow range, say from 0.90 to 0.96, that raw score is a really noisy and unstable signal for RL.
That's where they brought in the optional reward shaping. They basically stretched that tiny range out.
Correct. They mapped that score range to a standard 0 to 1 scale, and then, this is the clever part, they raise it to an exponent, like 3. By doing that, improvements that are closer to the best known value get a massively bigger reward.
So it creates this really steep learning curve right at the finish line where it's hardest to make progress. That makes a ton of sense. You're focusing the training where it's needed most.
And it absolutely worked.
Yeah.
Let's talk results. On circle packing, AlphaEvolve's best was about 2.63586. The EveEvolve, with its little 8B model, pushed it to 2.63598.
It might not sound like a huge jump, but in this world, changing that 6th decimal place is a major discovery. And the paper even notes that the solution it found was asymmetric, which suggests it found a whole new way of packing the circles, not just a small tweak on the old symmetric one.
And on the first autocorrelation inequality, it was the same story. It beat the previous best. The key takeaway is that across all the tasks they tested, the version with RL consistently got better results than the pure inference version, even with fewer tries.
Okay, so the RL definitely helps. But here's the billion-dollar question for anyone building agents. Did the model just get better at circle packing, or did it actually learn how to evolve programs? Did it generalize?
This is where my mind was kind of blown. They took a model checkpoint that had been trained with RL on circle packing, and then they ran it on circle packing again, but this time with the RL turned off pure inference mode.
Yeah.
It made progress way faster and got better scores than the original base model ever did. The RL training had fundamentally changed the model's parameters. It was now just inherently better at finding good program modifications.
But the real test is cross-task generalization.
This is the breakthrough. They took that same checkpoint, the one only ever trained on circle packing, and they threw it at brand new, completely unseen problems. The Hadamard matrix problem, the third autocorrelation inequality.
And it worked.
It matched or even beat the performance of models that had been specifically trained with RL on those new tasks.
Well,
yeah. I mean, the implication here is massive. Training a model in this dynamic ThetaEvolve environment seems to give it a general evolutionary capability. It learns the strategy of how to explore and improve code, and that strategy transfers to totally different problems.
Yeah.
It feels like a recipe for creating general-purpose LLM scientists.
that is huge. It's not just memorizing moves for one game. It's learning the abstract principles of how to play any game of that type.
Exactly. And they proved why their environment design was so critical. They ran a comparison against a more traditional RL setup, where the environment is static, where you always start from the same simple initial program.
And how did that go?
It was a disaster.
Yeah.
It performed way worse than even their simple inference-only baseline.
Why is that? Why is the dynamic environment so important?
Well, think about it. Trying to find the final, perfect, state-of-the-art program from a simple starting point in one leap is almost impossible. The probability is tiny. So if you only reward that final success, the agent almost never gets a positive signal to learn from.
It's like trying to teach a kid to climb Mount Everest by only giving them a cookie if they reach the summit on the first try. They'd never learn.
Perfect analogy. That's the static environment. The dynamic environment, with its huge database of good but not perfect programs, is like setting up a series of base camps. It rewards the agent for making incremental progress, for getting to the next base camp, and the probability of finding the next small improvement is way, way higher than finding the final solution from scratch.
So the database acts as a memory and a curriculum, breaking an impossible problem down into a series of smaller, solvable ones. That's what provides the rich training signal.
Absolutely. So ThetaEvolve isn't just another paper on code generation. It feels more like a blueprint for building agentic systems that can tackle long-term, complex scientific goals and do it efficiently and in the open.
It really proved that you don't necessarily need a massive proprietary model to push the state of the art. A smaller model can do it as long as you teach it how to learn the right strategies for evolution.
And it highlights that this structure coupling RL with a dynamic, verifiable environment and a big program database is probably going to be critical for the next wave of agentic AI.
Which leaves us with a really interesting final thought for you to chew on. Since the model learned a general skill that transferred between different problems, why stop there? Why train it on just one problem at a time? What could you do if you trained a single model on multiple different optimization tasks at the same time?
Could a multitask RL curriculum running on these dynamic environments create something truly amazing? A general-purpose LLM scientist that can approach any new problem with a pre-trained, battle-tested strategy for discovery. Something to think about.